So getting to our first example here, Department of Education, a researcher with the Department of Education followed with a cohort of students who graduated from high school in a certain year, monitoring the progress the students made towards completing a bachelor's degree. One aspect of his research was to determine whether students who first attended community college took longer to attain a bachelor's degree than those who immediately attended and remained at a four-year institution. Now, before we look at the data, what is the response variable in this study? What is the explanatory variable? The explanatory variable is the bit about whether or not someone attended community college first, and then the response, how long it took to graduate. Now, looking at the data, looking at our sample sizes, the larger of those two is 1,152. Well, if you think about all of the people that attend college, community college or four-year institution, one institution could have, I attended for undergraduate, a very small one. There was maybe between 700 and 900 there in any one particular year. But consider all of the colleges across the country. You're talking about hundreds of thousands, millions of people studying in college during a particular year. And so what would be 1,152? What would that be 5% of? Kind of going backwards here since we don't have a population size given, but 23,040. There are universities that have 20,000 to 30,000 students. Okay, so it seems reasonable that the sample sizes are not more than 5% of the respective populations. Both of those were at least as big as 30. We are not told whether we have simple random samples from those two populations, but hopefully the researcher with the Department of Education did do that. And do the bit with independent sampling. So let's see, can we say normally distributed is the time to graduate normally distributed? Even if not, again, the sample sizes are at least as big as 30. Okay, selected them all. Let's see if they agree. Okay, well, let's just see what we're being told here. What have I missed? Should not have included E. Okay, well, at least we had large sample sizes so that the central limit theorem would start to kick in. Okay, null hypothesis that they are equal, in other words, no difference, versus community college students taking longer to attain, so greater than. In other words, the mean time to graduate for a community college student minus the mean population mean time to graduate for someone who went straight to a four-year institution would be greater than 0. Calculate the test statistic. Okay, so my guess is that since the community college students were listed first, that we're going to use that as population 1. We first subtract the sample means in that order. And then our standard error, 1.179 squared divided by the 269 plus 1.014 squared divided by the sample size associated with that, 1,152. So I divide the 1.01, no rounding of that, divided by this, the standard error, no rounding of that. Now they want that rounded 2 decimal places. That's going to get rounded to 12.97. Now that seems to me to be pretty large. The degrees of freedom. We had 269 versus 1,152. If we take one less than each of those and then the minimum, that would be 268. But let's see here. They give us a significance level. Okay, scrolling back up, I can see when we were asked what the null and alternative hypotheses were, that we're using the alpha equals 0.05 level of significance. So that's this column right here. This is a one-sided test, a right-tailed test. So I do not need to divide alpha by 2. Again, when we take 1 away from each of those sample sizes and subtract 1, the minimum of those 2 is 268 degrees of freedom. So, problem is when I look at the 0.05 column, there's no 268 degrees of freedom listed. The first thing I'm going to try, since 268 is between 100 and 1,000, I'm going to try out the lower degrees of freedom, 100, to give me the critical value of 1.660 in that column. That is more conservative, which would lead to, if we were doing a confidence interval, bumping up the margin of error a bit so that we would really have the confidence level that we're supposed to have in between. On the other hand, by choosing that as a critical value in a hypothesis test, I'm being more conservative. Again, 268 is not listed. See how the one with a higher degree of freedom has a lower critical value? That happens as you go down any one of these columns. The larger the sample size, the larger the degrees of freedom, the lower the critical value in any column. So by saying 268 is in between here and going with the lower degrees of freedom, 100, using 1.660, I am being conservative, playing it safe. Okay, that apparently was what they wanted me to do. Should the hypothesis be rejected? Well, our critical value of 1.660 compared to 12.97. Give me a moment here. Okay, alpha was 0.05. So we're talking about, would we get a calculated t-value that is, its absolute value is so large that we are talking about something that is extreme or unusual if the null hypothesis that there is no difference mu1 minus mu2 equals 0. Equivalently, mu1 equals mu2. If it's true that there is no difference, then what's the probability we would have obtained those samples? If it's really low, if it's less than alpha equals 0.05, then we would reject H naught. Well, here's our critical value. And our calculated t-value, also positive, is further to the right. So don't take this to mean that this is to scale. It just matters that it's further right. It's in that critical region. That's telling us then that P is less than 0.05. And so we should reject the null hypothesis. Before I enter that, you need to know what the t-value is before you use TCDF. And we had a finite lower bound of 12.97. So then going infinitely to the right. And now I could actually use the 268 degrees of freedom because I'm using technology. That means that after the decimal point, you would have 29 zeros. That 1 at the beginning of this would show up at the 30th place after the decimal points. So that is definitely less than 0.05. Now, one more thing. You couldn't see it, but there was not a dash T on that question. It let me open up the table where I could find my critical values. And even though 268 degrees of freedom was not listed, I was able to use the more conservative approach and say, okay, well, I'll go with 100. Well, what if I use this formula, which the author of the textbook I'm currently using says after we use it, we have to round down to the nearest integer, regardless of what we see in the 10th place. And it's used for more precision in the p-value when using computer software. And that would include using the TI-84. So it's going to take careful use of parentheses. So sample size, sample standard deviation from the first squared divided by sample size plus sample standard deviation of the second getting squared divided by its sample size close the parentheses, square that, then parentheses around this entire denominator. So now we have S1 squared over N1 squared. All that divided by N1 minus 1, so 268, plus, okay, do that again for the second, 1.014 squared divided by N2 was 1152, close that and square it, and divide by 1 less than the sample size there. So we're getting something much higher. Round that down to 366. And if I repeat what I did with TCDF, I'm getting something even smaller. Now, after the decimal point, you've got 31 zeros, and that 3 is not showing up until 32nd decimal place. So, right. Anyway, we look at it, we're coming up with something where P is less than 0.05. So rejects. We do have evidence that the community college students take longer. we're thinking about the population of all community college students compared against the population of all that goes straight to a four-year institution, that on average, they do take longer, the community college students do. Now, a confidence interval. This could be a little different. Let's see here. What level do they want? 90%. Okay. 100 minus 90 divided by 2. Give me 5. And that's 5%. So go with 0.05. We actually looked up, because we're using alpha equals 0.05. We found the critical value then that would go with the confidence interval, 1.660. And so we're going to have the difference of the means from back here minus that critical value times, I'm not sure I'm going to be able to do this copy and paste, but I'll try it. Here was our standard error. That should be our lower bound. Switch it to addition, and we should get our upper bound. And they want us to round to 3 places. So 0.881, since the 7 in the 10,000ths place would round this up to a 1 in the thousandths place. 0.881 for lower bound. And 1.139 rounds down. Now, the answer to this is yes from part C. Should be going for one more example here soon, but that's it for this example.